Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
We have some exciting news.
Yes, we do, and I hope that it's not that I'm pregnant, because that would be a modern medical marvel and a huge surprise for me for multiple reasons.
Yes, it's not that, but we started a Patreon page.
I originally thought this was related to champagne, and wasn't sure how it tied into Failurology, but I've now learned it has nothing to do with champagne. We have a list of failures we want to tell you about, but we haven't been able to dig up enough information to cover a full episode.
So, on our Patreon page, we're releasing mini failure episodes.
The failures didn't do enough failing to warrant a full episode, which is great because some of these failures, they failed pretty spectacularly. They just didn't generate enough content for our regular episodes.
These mini failure episodes are also just the failure. No news and no fake ads. It's like Failurology Light.
They're going to come out on the opposite week from when we release our regular episodes, so you can have a Failurology episode, even if it's a tiny one, every week in your life.
Pretty exciting stuff. For $5 a month, Failurologists will get access to these mini failure episodes as well as future bonus content we develop, which we have a lot of ideas for, but we have to start somewhere.
Our first mini failure episode is up now, and it's about Lake Pegnier in Louisiana, which drained into a salt mine in a matter of minutes, which is pretty spectacular. In fact, it failed as spectacularly as it sounds. So check out the show notes for a link to our Patreon page.
I'm really excited about these failures because there are some really, really interesting ones that we've come across and we would love to cover, but the information's really limited. And so these mini failure episodes are allowing us to tell these stories. Specifically, the first episode, that Lake Pegnier, I've wanted to tell that story for months, but I can't find enough information to really cover an episode. And so I'm really glad that we have this outlet. I'm excited.
I think the mini failure episode probably takes longer than the actual lake draining into the salt mine.
True story. There's a video of it that we give links to in the show notes. It's very interesting. Very, very interesting.
And the video's not even sped up. That's how fast it happens.
Yes. So please go check out our Patreon. There's a link in the show notes. Come support our show. We'd love to see you over there. Yeah. So on to engineering news. Researchers have found a way to make ultra-thin surface coatings robust enough to survive scratches and dings. This is a new study completed at the University of Illinois Urbana-Champaign, and they found that rapid evaporative qualities of a specialized polymer containing a network of dynamic bonds in its backbone help form a water-resistant, self-healing coating of nanoscale thickness. The study was focused on boosting the efficiency of steam power plants by making the condenser surfaces more water resistant and efficient at forming water droplets, which optimizes heat transfer. In steam plants, with the heat and humidity, thin coatings can often break down in a matter of weeks or even hours, making them completely impractical. But conversely, thick coatings reduce heat transfer even though they're more durable. One thing that makes the thin coatings weak is that they form tiny pinholes as they cure, which is an opening for steam to penetrate and delaminate the coating. But the coatings they were studying have self-healing properties and are able to respond to pinhole defects or even scratches. The applications for this product are pretty much endless, but some of the major ones are in applications that require self-cleaning, anti-icing, anti-fogging, antibacterial, anti-fouling, and enhanced heat exchange coatings on this very, very thin, almost imperceptible coating, which is really exciting and interesting. And I'm glad that we're seeing a lot of self-healing products coming out lately. There's been some concrete, and now we've got this coating, and I'm sure there's many more that I just am not aware of. So this is really exciting. If you know of any, please send them our way. I love to read this stuff. It's very, very fascinating to me. So if you want to check out more about the study, there's a link in our show notes to the study and the news article that we found on it. So please go check that out. That's on our website at failurology.ca. Roberto Luongo's Bingo Bango Bingo Hall.
If you've had a bad day, come dab your troubles away.
Try it on for size. You could even win a prize.
Don't let this beach ball of an opportunity pass you by.
Find a Roberto Luongo's Bingo Bango Bingo Hall near you.
Now, on to this week's engineering failure. The Arecibo Telescope, a giant spherical reflector radio telescope located in Arecibo, Puerto Rico.
After construction of the telescope began in the mid-1960s, it opened on November 1st, 1963, as the world's largest single-aperture telescope for 53 years, until its collapse, of course. As Brian said, it's located in Puerto Rico as part of the Arecibo Observatory, which is about 100 kilometers west of San Juan. It was run by the University of Central Florida since 2018, but had been previously operated by various science and government groups over the years. The telescope's origins trace back to the US's late 1950s attempt to develop anti-ballistic missile defenses. And it was used for research into radio astronomy, atmospheric science, radar astronomy, and the search for extraterrestrial intelligence programs.
So the Arecibo Telescope, you might be familiar with it from the James Bond film GoldenEye or the 1997 sci-fi movie Contact.
The GoldenEye scene is fantastic. It's one of my favorites. It's right at the end. Bond slides down the dish with Natalia, and then he climbs up onto the platform and he fights 006. Although I do want to point out that the real telescope isn't hidden within a lake like it was in the movie. And sidebar for a second, this may be really controversial to say, but GoldenEye is my favorite Bond movie. It was the first one I saw. It's the one I've seen the most. I've honestly lost count of how many times I've seen it. I even had the GoldenEye game for Nintendo 64, which was really cool. It was the only game I would play besides Mario Kart, so that definitely says something.
GoldenEye is a great game for the N64. It was probably one of my favorite N64 games growing up, but the only chance I ever had to play it was at friends' houses. So that didn't go well for me at all, and it really started the trend of me losing 12-year-olds in video games, which has continued on to this day.
I've lost Angry Bird to a 3-year-old, so I understand your pain.
Yep.
How hard is it to fling a bird across the thing? It's not that hard, but they're just so much better at it than me. I don't know how they do it.
And they don't even really understand what's going on. They're just there for the music.
Exactly.
So the Arecibo Telescope, it scrutinized our atmosphere from a few kilometers away to a few thousand kilometers away, where it would smoothly connect the interplanetary space. And with its radar vision, the telescope studies the properties of planets, of comets, and asteroids. And within our galaxy, it detects really faint pulses, radio pulses that are emitted hundreds of times per second from pulsar stars. And from the farthest reaches of the universe, quasars and galaxies emit radio waves which arrive at Earth hundreds of millions of years later as signals that are so weak that they can only be detected by giant radio telescopes like this one. So it had a couple highlights or significant findings in its career as a telescope. Researchers at the telescope discovered the first extrasolar planets around the pulsar B1257 plus 12 in 1992. The telescope was able to produce detailed radar maps of the surface of Venus and Mercury. They also discovered that Mercury had a rotational period of 59 days instead of 99 days that it was originally presumed to have. And American astronomers Russell House and Joseph H. Taylor Jr. used the telescope to discover the first binary pulsar. They showed that this binary pulsar was losing energy through gravitational radiation at a rate predicted by Albert Einstein's theory of general relativity, and this eventually led to them winning the Nobel Prize for Physics in 1993, which is incredibly fascinating.
Very, very interesting. This telescope has definitely accomplished a lot. Spoiler alert, it collapses, but in order to better understand how and why, we have to first understand how it was constructed. So if you've seen GoldenEye, you have a general idea of how it was built.
And there are pictures of the telescope on the Failurology website, so if the explanation's a little bit confusing, the pictures help out a phenomenal amount.
Yes, they definitely do. I always look at the pictures while I'm researching. So there's a main collecting dish, also known as the reflector, which is essentially looks like a bowl at the bottom of the telescope. And it's 305 meters in diameter, and that was constructed inside of the karst sinkhole. It's more than 3 US football fields wide. This dish is huge. And the depth of the dish is 51 meters, which is approximately 14 stories.
I live on the 12th floor of my building, so the depth of this dish is 2 stories higher than the floor that I currently live on. Like, that is, I think I live fairly high up, and where I live wouldn't even reach the top of the dish. That is phenomenal.
It is, yeah. I live on the ground floor. It's safer down here. I like it better. But yes. The dish surface is made up of over 38,000 perforated aluminum panels, each one approximately 1 meter by 2.5 meters. The individually adjustable aluminum panels are supported by a network of cables that are strung across the underlying sinkhole. And these panels make up what is called a Gregorian dome. And they were installed in 1997 to replace the original 20 millimeter galvanized wire mesh that was originally laid on those cables. 150 meters above the reflector, above this dish, is a 900-ton platform suspended by 18 cables that are strung from 3 reinforced concrete towers.
And this is where 007 fought 006 in GoldenEye.
Yes, and 006, spoiler alert, falls off the platform to his demise. Well, in the movie you think that.
Spoiler alert.
Spoiler alert.
I hope we didn't ruin it for anyone. If you were hoping to watch it this weekend.
I think GoldenEye came out in like 1996. If you haven't seen it by now, that's on you. The reflector platform has a rotating bow-shaped track that was 93 meters long and called the azimuth arm. This carried receiving antennas and secondary and tertiary reflectors for the platform. Each of the 18 main cables that support this platform are bundled together from 168 centimeter diameter wires, with the bundle painted over, and dry air is continuously blown through to prevent corrosion due to the humid tropical climate. So this I actually found very, very interesting. So the cable bundle, the structural cable bundle, has some kind of duct or coating around it that allows air to pass through it so that they can make sure that there's no moisture buildup inside of the cable bundle. And the theory behind that is it would significantly limit corrosion. If you want to check out more on the cable, we've got a picture of it on the website. Check out the page for this episode.
Like Nicole mentioned, there's 3 towers around the sinkhole that would hold up the 900-ton platform. And the towers are backguyed to ground anchors with 7 8.25 centimeter diameter steel bridge cables. So fairly large diameter cables. Like that's a good sized cable. So there's one tower on the north side, and that tower is named T12, one in the southeast corner named T4, and one in the southwest corner named T8. So the tower names appear to be based on the position in relation to a clock face, which makes a lot of sense. So 12 o'clock would be at the north end, and then you kind of go around for the southeast to be T4, where the 4 o'clock number would be, and then in the southwest corner where the 8 o'clock number would be.
I thought that was a really interesting naming method for the tower. I haven't come across something like that before. Normally they're just numbered 1, 2, 3 is kind of what I expected. And so when I was reading about T4, which we'll get into later, I was like, well, there's only 3 towers. Why is this 4? And then I kind of looked at a map and I realized that they're like a clock, and I was like, oh, that's really interesting.
I've definitely named ground control points and other things on projects after clock faces. It works out pretty well, actually. So another system of 3 pairs of cables run from each corner of the platform to a large concrete block underneath the reflector. And these are attached to giant jacks, which allow adjustment of the height of each corner with millimeter precision, which is important since they're trying to observe things that are millions of kilometers away. So the millimeter precision is really important, just so they can accurately point the telescope or accurately figure out where the signals are coming from. So the little millimeter differences that we can make here make a huge difference in the ability to receive the signal and accurately pinpoint the signal that they're getting. So the dish would remain stationary, and the reflector moves on a series of cables depending on telescope positioning. So pretty similar to Skycam at sporting events. It shows up a lot in the NFL games when they'll do kickoff returns or if they're zooming in on a play. So a similar system to that existed in a telescope. Once radio waves from space hit the dish, they were collected by detectors in a dome above it, and the detectors could move along a cable above the dish. Again, if you're confused by this explanation, there's a couple pictures on the site that show this fairly well. The antennas are very sensitive and highly complex radio receivers, and they're contained in a bath of liquid helium to maintain a lower receiver temperature, which is important to minimize electron noise in the receivers, and that will allow better detection for very weak radio signals that come in from outer space.
On September 21st in 2017, high winds associated with Hurricane Maria caused the 430 megahertz line feed to break and fall onto the primary dish, which damaged roughly 30 of the 38,000 aluminum panels. So, all things considered, 30 is not that bad. And also, most observations didn't use this line feed, so operations could continue. But in order to fix this and restore service levels, it would take more than the current operating budget, and so unfortunately that never did get repaired.
Yes. So the way that the observations work, a lot of the antennas were set to a very narrow frequency band. So this damage just impacted the 430 megahertz line feed that was there. So at this current time, there weren't a lot of observations that were going on in that 430 megahertz line. So, like Nicole mentioned, they could continue observing other things. So it wasn't a huge impact right now, but things get a little bit worse.
Don't worry, it gets worse. On October 10th, 2020, an auxiliary platform support cable separated from Tower 4, causing damage to the telescope, including a 30-meter gash in the reflector dish.
That's really bad.
That's really bad. The damage included 6 to 8 panels in the Gregorian dome and to the platform used to access the dome. No one was reported to have been hurt by this partial collapse, but the facility was closed as damage assessments were made. The main support cables and towers had been designed with a safety factor of 2 to sustain twice the weight of the platform. But when the Gregorian dome panels were added in 1997, it was believed that at that time the cables would retain this safety factor. But due to uneven load distribution, that would be almost impossible to guarantee. As well, recent calculations and modeling of the structure found that the safety factor of Tower 4 had dropped to 1.67. That said, they still believe that the structure was safe, at least for the time being, until repairs could be made. I do want to mention, because I think it's important, that there were also periods of time where the fans that were blowing air through the cables were not operating, so there was a higher risk of corrosion during that time. They found in the 1980s and then again in the 2010s that some of the molten zinc, which affixes the cable to the socket at the tower, was not complete, which allowed moisture to penetrate the wire bundles and again increase corrosion. So there was a few different points of increased corrosion risk.
Yeah, and I'm assuming that they couldn't do any sort of internal corrosion inspection on these cables, or they didn't have a good way to inspect, corrosion in these cables as a structure age. Because remember, this was built back in the 1960s, so we're into the 2010s, so we're looking at something that's been around for 50 plus years at this point.
Yeah, and I don't think that the original design had incorporated a lifespan cycle for these cables, and so I don't think they really had any idea or concept of how often these cables would need replacement. And even if they did have an idea of that, it definitely sounds like they didn't have the budget, because even making the repairs that they've had so far seemed almost impossible to get accomplished just because the budgets were so tight. This telescope, although it does a lot of really cool things, the main purpose that it's built for is, which is military defense. That type of tool is no longer required. There's other methods that they use to detect those types of things. And so I think that's a big thing. Getting money for science is hard. So that was definitely a challenge. That said, they made plans to replace all of 6 auxiliary cables from Tower 4 at a cost of $10.5 million US.
Which is not an insignificant amount. Like $10.5 million is a good chunk of money for essentially replacing cables.
Yeah, and I'm kind of impressed they came up with it. But before that could happen, a second cable broke on November 7th, 2020, and shattered part of the dish. The National Science Foundation announced that the telescope was in danger of collapse, and the cables could not be safely repaired. On November 19th, 2020, after reviewing proposals to stabilize the telescope or reduce the weight of the platform, it was announced that they would decommission the telescope. On December 1st, 2020, the final cable from Tower 4 snapped, causing the platform to crash into the side of the dish. Leading up to this, the cables supporting the towers had been failing at a rate of 1 or 2 a day, which is significant. And when the platform collapsed, the backstay cables on the remaining towers, which had been adjusted to provide more support away from the dish, they were pulling the towers back, but the platform was pulling the towers in. And so the towers were staying kind of, stationary in the middle. But once the dish let go and that force pulling them in was no longer there, the tower snapped back. And it caused damage to some pretty significant damage to those towers as well. One of them even caused minor structural damage to other buildings on the campus. The cables that failed in November dated back to the observatory's construction in 1963. So these were original cables. As I said before, the socket joint design did not establish the end-of-life capability. There are really good videos of the collapse from the ground and air viewpoints. They had a camera on the ground, and then they also had a drone in the air, which I'm really curious, Brian, do you know, did they just have a drone there 24/7 or...
I think after it initially collapsed, because remember, after the, kind of this first significant, failure happens, it doesn't take too much longer for the other failures to happen. So I think the drone was probably there just as an investigation thing, or maybe they knew that there may be a potential failure that was imminent, and just decided to have a drone on site or on standby close to the site that could be put over the project site. I didn't see anything specifically related to why the drone was there when I was doing research for this episode, but again, since the structure is so large and it probably has limited access to walk across it, for investigation purposes, they may have just used the drone as a tool in their investigation.
The only reason I asked was because the drone was at exactly the right point, at exactly the right time that the cable started to give, which is just an impressive coincidence.
Yeah, or they may have had some sort of monitoring devices on the cables, and they were able to move the drone over there. But either way, now there's drone footage of the cables collapsing and bad things happening at the telescope.
We'll put a link on the episode page on our website at failurology.ca. So if you could go there and you go to this episode page, you'll see links to this video as well as all of our other sources. One other thing that I think is important is the design factor of safety, which, yes, was double the weight of the platform, was still significantly less than the minimum suggested and didn't really ensure any structural redundancy in the event of a cable failure. So to me, again, not being a structural engineer, in a scenario like this, you want at least an N+1 scenario. So you want to have one tower completely catastrophically fail and have the other two towers be able to support the platform, or perhaps you're not relying on the towers. Maybe you need all three towers, but perhaps the cables from those towers can some of them can fail and the platform still stays standing. And that redundancy, at least to the extent that it would in other telescopes like this, did not exist here.
Yeah, I would have thought that they would have designed something like that into the telescope, but I guess they didn't, which is one of the reasons that this failed. So NASA actually came up with a report of findings, a summary of findings, in June of 2021. It's fairly long and fairly detailed, so we attempted to summarize it as best we can for you. But before we get into the findings, from the executive summary of this report, I think there's a really good quote that kind of encompasses the entirety of the failure. So this is a direct quote from the Arecibo Observatory Auxiliary M4N socket termination failure investigation. So they say, the NASA aerospace team concludes that the most probable cause of the AUX M4N cable failure was a socket joint design with insufficient design criteria that did not explicitly consider socket constituent stress margins or time-dependent damage mechanisms. The socket attachment design was found to have an initially low structural margin, notably in the outer socket wires, which degraded primarily due to zinc creep effects that were activated by long-term sustained loading and exacerbated by cyclic loading. Additionally, a few wires showed evidence of hydrogen-assisted cracking and wire surface defects that may have contributed to initial outer wire failures. End quote. So like we mentioned, it sounds like there were a couple things that were going on that led to the failure of the cable that was supporting pieces of this telescope. So during the investigation, wires were traced and labeled to indicate whether they had fractured or whether they had slipped from the socket and their location of termination. Of the 126 cable wires, 56 fractured within the socket, and 70 did not fracture, instead pulling free of the socket joint. So of the 56 that failed, 5 had surface defects running along their lengths, and 2 of those defects likely contributed to the failure. The cable section that pulled free from the socket joint had 94 wires still encased together in zinc from the socket cavity, and in the report this is referred to as the cable zinc slug, meaning that 32 wires were not in the socket cavity. So additional examination of the wires from the failed cable showed that of the 94 wires in the cable zinc slug, 26 were fractured wires that made it to the fractured wires in the socket, and 68 were intact wires that did not fracture. Of the 32 remaining cable wires not accounted for in the cable zinc slug, 30 wires were fractured and made it to the fractured wires in the socket, and 2 were intact wires that did not fracture. All 32 wires were outer ring wires. In other words, 0 to 2 intact wires pulled free of the socket individually, and the other 30 to 32 outer ring wires came free of the cable zinc slug due to insufficient surrounding zinc and/or from the forces after core pullout and subsequent impact. Also, as wires and slug failed over time, the loads were redistributed to other wires, and several wires showed brittle failure which can occur under high impact loading. While some corrosion protective measures were put in service during the life of the socket, for example, some mastic coating on the casting cap, these measures were put in place after corrosion had begun and were not adequately maintained to provide continued corrosion protection over the life of the socket. This resulted in pervasive quantities of corrosion product, particularly zinc oxide, throughout the socket along various identified moisture pathways. In summary, failure of the outer wires occurred prior to total cable collapse, and the outer wires were critical in maintaining the function of the socket joint, and the outer wires were highly stressed with minimal structural margins of safety.
So yeah, I think there's a lot going on there. The socket joint, it definitely sounds like there's a problem with how the wires fasten inside of that, but then there also seems to be lifespan issues, redundancy issues,
some corrosion pathway issues for
corrosion
where
issues,
moisture could get in and lead to some corrosion, that may or may not have been able to be inspected. So yeah, I think over the life cycle of the telescope, there were just some chronic issues that crept in and led to ultimately the failure of one of the cable bundles, and that led to more and more failures of cables as they couldn't support the loads that they were required to support.
Yeah, and I mean, again, not structural engineer, but I'm kind of impressed it lasted 60 years, if I'm being honest.
60 years is a really, really long time for anything, of this nature to last. I mean, we're talking about a dish that was 1,000 feet across and 3 football fields. It's 14 stories deep. It's got 38,000 plus panels on it, and things were moving in it, and it was observing stuff in space or from space for 60 plus years. I mean, that's really, really impressive.
Very impressive. So a few things have happened since the collapse. As we've mentioned, there are similar telescopes, one of them being in China, and China stated that they would start taking applications for international researchers to use their telescope in 2021. In late December 2020, so not even a month after this collapse, the governor of Puerto Rico signed an executive order to remove debris and design a new observatory in the telescope's place. This order also designated it a heritage site, which I think is important because that offers the site access to additional resources and funding that they otherwise wouldn't have. And I also agree that this is a heritage site. As we just said, it was doing some really cool things for 60 years, and I think it deserves to be preserved. And luckily, there are plans already being developed, not officially going ahead, but they're looking at it and talking about it, to replace the site with 1,000 closely spaced 9-meter wide telescopes that are mounted to a flat plate over the sinkhole, which sounds really cool. So it's almost like a mini telescope farm in comparison to what was there before. So instead of one giant telescope, you have a square of 1,000 closely spaced telescopes. So while the telescopes themselves would be fixed, the plate could move. And based on advances in telescope design, as well as the fact that they would all be on a plate that moves, these telescopes could potentially see 500 times the field of view of the original. So as devastating as the collapse was, if they do build something like this in its place, this is almost a silver lining, if you could say. I think there's some really cool potential for that site, and I'm excited to see what they come up with.
Yeah, that does sound really neat, and it kind of preserves the value or the use of the site, where it'll still be conducting space-based observations or conducting observations of space. It's just kind of maybe more modern technology and a little bit better way to do things.
Yeah, and if I understand it, the telescope is on a campus of some kind. I believe it's Central Florida University had taken over the telescope, so I would assume that it's their campus. So there's lots of other things going on there besides just the telescope. And so replacing the telescope with something similar would allow that campus to continue to thrive instead of having to now find a new location to relocate all of that stuff or to cancel completely. I mean, we definitely don't want that. We want to keep learning. We want to keep growing. We want science to progress. So I think finding a way to rebuild here would really be beneficial.
Yeah, because there's probably a bunch of supporting industries for researchers down there and other campus activities like you mentioned that are kind of tied to deep space exploration or the SETI program or just other space-based observations. So yeah, to have a similar theme there would I think be beneficial to kind of the tertiary uses of the site.
Yeah, but it's still early days. I mean, the telescope collapsed less than a year ago. I'm not even sure they've managed to clean up the site yet, let alone started talking about how they're going to rebuild. But I don't know. We're going to keep watching and we'll see. And hopefully we can feature it in a news article soon.
Yeah, that would be neat. We could do an engineering news episode about a failurology episode that we covered or a continuation of a failurology episode. That would be really neat.
Yeah, it would.
Well, so there you have it. A combination of small safety factors, questionable maintenance, and unfortunate weather and timing led to the collapse of the Arecibo Telescope before it could be safely repaired or decommissioned. Luckily, no one was hurt, and who knows, they could end up replacing it with something way better that they wouldn't have done if the telescope was still functional.
For photos, sources, and an episode summary from this week's episode, head to failurology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failurology so more people can find us. If you want to chat with us, our Twitter handle is @Failurology. You can email us at thefailurologypodcast@gmail.com, or you can connect with us on LinkedIn. Also, please check out our Patreon so you can hear more of our mini failure episodes that we'd love to share with you. Check out the show notes for links to all of these. Thanks everyone for listening, and tune into the next episode where we'll talk about Apollo 1, the space program that eventually led to Americans walking on the moon. Bye everyone. Talk soon.